Hi, everyone. My name's Colette Salick. I am an astronomy professor, and today I'm going to talk about one of my favorite topics, which is planets. And in particular, I'm going to tell you about planet formation, and then I want to tell you about the James Webb Space Telescope, which I'm really excited about. So what I'm going to do in this talk is I'm going to first walk you through some of the basics of planet formation, what I call the planet formation fairy tale. So what we think um, happens when planets form, but then I'm going to tell you why this story is not everything and why it's incomplete. And I'll give you a little bit of insight into how we try to complete the story by actually studying planet formation with telescopes. And then I'm going to finish up by telling you about the James Webb Space Telescope, which is kind of the newest toy we'll get to play with to study planets. So here's the standard fairy tale for planet formation. And if you've taken an astronomy class, they might have told you about this. So um, it turns out that things in space that have to form into planets are really, really tiny. They're about 1 micrometer in size. So that's about the size of dust. And those have to somehow all stick together to form planets. So that process is still not fully understood. But somehow the little pieces stick together by colliding and sticking. When they get big enough, about 1 kilometer in size, then gravity can also help. And then things get ever bigger until they get to be something like 1 to 10 Earth masses in size. At that point, planets have to make a decision, and we'll describe what that decision actually entails in a minute. So some of them will become terrestrial planets like Mercury, Venus, Earth, Mars, and those stay at sort of the 1 Earth mass or even smaller size. But some of them will get a little bit bigger and they'll actually attract a whole atmosphere of gas on top of them. And those will become the gas giants, Jupiter, Saturn, Uranus, and Neptune. But that can't be the whole story because if we look at the solar system, it looks like this. So sort of. So this is a picture where all of the sizes of the planets are accurate and their colors are correct. What's not correct is the distances between them. So space is really, really spacious. So there's usually, there's actually a lot more space in between these planets. But what we see is that the planets look all different. We have the terrestrial planets, the really small ones. We have the really giant gas giants. We have all these different colors. And that turns out to be really meaningful. So it's not a coincidence that the planets are all of these different colors. So here's the standard fairy tale for explaining the different types of planets we get in the solar system. So here's a little emoji guy to help us out. If you're close to the sun, it's really hot. And if you're far from the sun, it's cold. So you can see here with the little emoji that first he is sweating. And then as he gets farther from the sun, that sweat actually turns solid into little snowflakes. So this is sort of what happens in the solar system, except in the solar system, in the early stages, we have very low pressure. So things don't exist really in the liquid phase. So everything transitions from gas phase to solid phase. But if you're close to the sun, then things are more likely to be gases. And if you're far from the sun, they're more likely to be solids. And what does that have to do with the formation of planets? Well, if you form your planets with this standard story that I told you, where you put all your solids together first and then put your atmosphere on later, then what you form your solid body out of is all of the things that are in the solid phase at that place in the early solar system. So let me give you some examples. So here's, for example, let's say Mercury. You're very close to the sun, it's very hot. So many, many things will be in the gas phase. And so only a few things will be available to form Mercury's body. And that's things like metals or very rocks that really like to be in the solid phase. march out to Earth's location, so a little bit cooler. And now things like the rocks we're used to seeing on Earth will be available to form Earth. So things like olivine or quartz, that will be available for Earth. March out again to Jupiter's location. That's actually 5 times farther from the sun than the Earth. At Jupiter's location, water becomes solid as well. And then march out to, let's say, Neptune, and you start to incorporate things that we think of on Earth as being gases, but in the solar system, we think of them almost as ices. So these are things like methane and ammonia. So if you do the math, this scenario does actually an amazing job of predicting planetary compositions, and it can do this at really a pretty minute scale, predicting all the mineral abundances in the solid planets, and it's known as the condensation sequence. And it has another important consequence as well, and this comes back to, we mentioned how water freezes out at Jupiter's location. So why is that important? Well, if you freeze out water, then you suddenly, there's so much water in the early solar system that you suddenly have way more solids, and you can actually grow a much larger solid body. And so this comes back to, I said the planets make a decision about whether to become a gas giant or a terrestrial planet. Well, this decision might actually be whether or not the solids have water available as a solid or not. If they do, they'll grow a lot bigger, and then they'll have the ability to gravitationally attract a large atmosphere. If you ask where this happens in the solar system, it's actually very interesting. The water freezes out right between Mars and Jupiter. So maybe not a coincidence. So that's the fairy tale, and they lived happily ever after, the end. But maybe not. So let me tell you about some of the issues, some of the little holes that are in this fairy tale. So I want to show you, this is not a very picturesque slide, but it's really important, so I'm going to show it anyway. So this is actually the abstract from some of the original work on the condensation sequence. And the abstract says, so the distribution, very technical, the distribution of the major elements between vapor and solid has been calculated for a cooling gas of cosmic composition. So what does that really mean if we tease it out? So interestingly enough, cooling gas actually means that the solar system was originally very hot. And if you know any chemistry, what hot means is that the chemistry can actually come to equilibrium. And if you ask what cosmic composition means, it means, well, it means that the whole solar system had the same composition as the sun. But that implies that if the whole solar system has the same composition as the sun, then you need to have everything be well mixed. You can't have little pockets of different types of chemistry. So this means that the solar system was well mixed. Problem is, if these assumptions don't hold, then the whole condensation sequence is not the whole story. So I want to give you a little taste of how this might differ. So here's a tale of 2 carbon atoms. So let's say you have a carbon atom in its very early solar system stages. It's in the form of graphite, which is a solid. So in the condensation sequence, everything's going to heat up quite a bit. So likely this graphite is going to vaporize. And if you have a carbon atom sitting out in space and there's oxygen around, it's going to combine and probably form carbon monoxide. Carbon monoxide really likes to be in the gas phase, so it's unlikely to become part of a planet, and it's probably going to get blown away into space. Okay, that's the condensation sequence, but what if you don't have things get really hot? Well, maybe the graphite just stays intact. It stays as a solid. If it's a solid, it becomes part of the building blocks of a planet like the Earth. So these are 2 very different scenarios for this one atom, but now imagine a whole collection of atoms and how these differing paths could produce very different solar systems. So what I try to do in my work is really try to figure out how true is this fairy tale story. So is it the case that the whole solar system was at one point hot, or is it possible that parts of it were hot and parts of it stayed cold? To what extent was the early solar system well mixed? Was there mixing between the hot and cold parts? Was there mixing up and down? Or were there pockets of different materials? And thinking outside of the solar system, we can also ask, well, is the solar system representative of everything that's out there? And this slide is meant to just give you a little taste that the answer is definitely no. The solar system does not represent everything out there. And so these are actual pictures of what we call protoplanetary disks. These are the forming environments that planets form in. So the birthplace of planets. And these are just 12 that happen to be imaged in the Taurus molecular cloud in the Taurus constellation. And you can see that they all look different. So every planet forming region has really its own personality, and it's likely to form a very different type of solar system or planetary system in the end. So what is the true history of the solar system, and does every planetary system have the same history? Obviously, the answer is probably no. But what are the different types of histories that these planetary systems can have? So if we want to measure the planet forming environment, we need to actually directly look at it. So that's what I do for my work. I actually directly measure the chemistry and try to figure out what chemical processes are occurring in planet forming regions, these protoplanetary disks. So the main technique I use is spectroscopy. Spectroscopy is the splitting of light into different colors, and it's the primary means to study chemistry. And the reason is the following. So let's say you have a molecule. Here again is CO shown. So the molecule has a bond, and so it actually vibrates and it also rotates. And the vibration and rotation are associated with certain energy levels. And quantum mechanics actually says that the energy levels are what we call quantized. So they have fixed values. And if a molecule, let's say it's vibrating very fast and it decides to lose a little bit of energy, it can move to a slower state, but it's going to release a photon or a particle of light that has a very defined color. And the same with rotation. So it can, let's say, be rotating very, very quickly, decide, okay, I'm going to rotate a little bit more slowly, and it will emit a photon, a particle of light that has a distinctive color. So here's what it looks like in reality. On the left-hand side is the energy level diagram for carbon monoxide. So basically, each one of these little horizontal lines represents an energy level that the molecule can choose to be living in. But then it can also choose to kind of drop down to a lower energy level. And that's what those arrows are showing. And every time it does that, it emits a photon that is a defined color. And color in science, we call that the wavelength of the light. So on the right-hand side is a more technical plot. So this is showing the brightness of light that we would see from a protoplanetary disk that has carbon monoxide in it. And what you see is on the x-axis is the color or the wavelength. And then you see all of these little spikes. And each spike is associated with one of those arrows on the left-hand side. So each spike is one distinctive color that comes from a carbon monoxide molecule. So these spectra serve as fingerprints of different molecules. So a lot of the real pioneering work in this field happened with the Spitzer Space Telescope. It has a spectrograph called the Infrared Spectrograph, IRS. And here's just one example of one of the discovery spectra showing some molecules that were found in planet-forming regions. So on the top, you can see the actual spectrum. And then on the bottom is a model showing the detection of some simple molecules, things like CO2, HCN, C2H2, water, and so on. And you can see in the upper left, actually, that is the telescope before it was launched into space. And if you look carefully, you'll see a human. So it gives you a little sense of scale there. Many ground-based telescopes played a role too. This is lucky for me because I got to travel to some awesome places like Hawaii and Chile. Okay, but now I want to get you excited about what's really next in this field, and that is the James Webb Space Telescope. So here's a little artist's cartoon of it. So this is known as JWST for short. So what kind of telescope is this? You may be familiar with the Hubble Space Telescope, known as HST for short. And this is very similar in a lot of ways to Hubble in that it is an all-purpose telescope. So it's meant to do all different kinds of astronomy. But as compared to HST, JWST is much bigger, and this is really important. So here they are to scale. The diameter of the HST mirror is 2.4 meters, while the diameter of the JWST mirror is 6.5 meters. And why does that matter? There are two main benefits to size: greater sensitivity and sharper images. Just as an aside, so because JWST is so large, it actually has a little bit of trouble fitting into its rocket. So it's going to be launched in an Ariane 5 rocket. And in order to fit, it actually has to kind of fold itself up. And so I think of JWST as kind of a transformer. And this is some homework for you. I know you probably didn't think you'd have homework, but you should Google the JWST deployment animation and watch the whole sequence of events that it has to go through to get into space and then unfold itself into the telescope. So look that up, don't miss it. So HST and JWST also have very, very different orbits. So the Hubble Space Telescope, it was actually launched on the space shuttle, and it now orbits in basically a low Earth orbit. So it's not very far from the surface of the Earth, astronomically speaking. And that's not at all true for JWST. JWST is actually going to go 1.5 million kilometers from the Earth. So this diagram here, although I think it's a cool diagram, it is very much not to scale. So James Webb is going to be way further from the Earth than this picture kind of represents. And it's in this special spot called a Lagrange point. You can see in the bottom of this plot here. So it's over here at this spot called L2. And what that does is it's a special spot where all of the forces on the spacecraft are going to balance out so that as the Earth goes around the sun, the spacecraft will always remain in line with the Earth. So that's good for a few reasons. First of all, you don't have to use a lot of fuel to kind of keep it in place. It'll always be able to communicate with the Earth, so it'll be sending back data all the time. And it also kind of makes for a stable environment, so the amount of light from the sun doesn't vary very much with time. It also, because it's very, very far from the Earth and the sun, it has a very different environment than HST has. So HST in low Earth orbit essentially operates at room temperature, while JWST operates much, much colder. So here's a little cartoon version of it. So it's something like minus 233 Celsius or minus 388 Fahrenheit. Can't even imagine that. So that was the cartoon, but I wanted to show you what it actually looks like in the lab. So here is the sun shield of the telescope, and you can see some humans for scale. And so you see the sun shield is very large. It's many, many layers that are meant to keep the side of the telescope that's away from the sun cool. Actually, on the side of the telescope that's facing the sun, it has solar panels that use the sun for power. So what is the point of operating at these cold temperatures? Well, JWST can really do much better in the infrared. So it can perform infrared observations, which HST was not very good at. So this actually makes this a successor to the Spitzer Space Telescope, which I told you did a lot of the pioneering work on chemistry in planet-forming regions. So just to show you how this compares to Spitzer, so Hubble was smaller than James Webb by quite a bit, but Spitzer is really, really tiny, only 0.85 meters in diameter. So this telescope is just going to give us so much more sensitivity and sharper images than Spitzer did. So let me actually show you some data so you can get a little sense. So here's another spectrum. On the y-axis again is, so this says signal, or you can think of it as brightness, and on the x-axis is color or wavelength. And here I'm showing in gray a Spitzer spectrum, infrared spectrograph from Spitzer. And you can see, I mean, if you're not a spectroscopist, you don't know what you're looking at, but I can tell you can see all these wiggles that are signatures, fingerprints of certain molecules like water and HCN, acetylene. But here's what it's going to look like. This is a simulation for JWST. And it's just, for my eyes, spectacular. You can see all of these lines just shooting up. They're really easy to detect. They're very sharp. And they're just so much cleaner than what we saw with Spitzer. So what do we do with this? Well, we can better study the molecules that we've already detected. And I could give you whole lectures about what we still have to do with the data we've already looked at. But we can also discover new molecules, and we can discover new isotopologues. That just means molecules that have different isotopes of atoms in them. And because of the sensitivity of JWST, we can also look at fainter solar systems. And a couple of things that are particularly interesting, one is to look at different parts of the galaxy. So far we've been limited to sort of the nearby regions of our galaxy. But if we want to look at totally different environments, we're going to need to step further out in our galaxy. And the other direction that's really interesting is looking at different types of stars. So not just sun-like stars or brighter stars, which we've been limited to so far, but also at very small stars, which actually make up the majority of stars in our galaxy. So understanding how planet formation might change if you have a different type of star is something that we have yet to explore. Okay, so I hope I got you excited about planets and about JWST. So I'll just leave you with this, that you should stay tuned for the JWST launch. It was March 2021, but unfortunately, due to the global pandemic, it's now TBA as of the date that I'm making this video, but there should be an announcement shortly about an updated launch date. So you may even know the launch date by the time you see this video. So stay tuned, and thanks for listening.